Okay, so we are now on part 2 of section 7.4. We're going to continue on with partial fractions. We're going to need, so before we continue, so we saw last time how to divide polynomials, and that, if the degree of the numerator was higher than greater than or equal to the degree of the denominator, we were able to do that and get, something that was easier to integrate. So now we're going to look at cases where the degree of the numerator is less than the degree of the denominator. We're going to have to use partial fractions. So we're going to need some ideas from algebra first about polynomials. So any polynomial, so the main idea that we're going to need is any polynomial can be factored into irreducible factors. I'll explain what irreducible means in a second, of the form ax plus b or ax squared plus bx plus c. So what I mean by irreducible is it's not, so any polynomial can factor into irreducible factors of the form. I'm going to write over the reals just to make this a little more accurate mathematically. I don't want to, so it doesn't matter for what we're doing, but I don't want to write down anything that's wrong. So the idea is, I can put any polynomial into factors that look like this, so they are linear factors, or if they don't have real roots, I'm going to be able to split it up into a quadratic. And the roots of this quadratic are actually going to be complex numbers, but they're going to be complex conjugates. So if you remember what that is, that's good. We're not going to need to factor those, so it's not really going to matter. So we're going to use that to be able to do the partial fractions decomposition. So the idea behind partial fractions is, if I have two polynomials divided by each other, so if I have p of x divided by q of x, I can factor q of x. I'll be able to factor q of x into, I'll be able to factor it, so q of x is equal to, a1 x plus b1, a2 x plus b2, and the a's and b's don't have to be different. We could have, powers. So like you could have an ax plus b squared, so on and so forth. There might be an a kx squared plus bkx plus ck, and so forth. So with this, the idea is, if I have a rational function, I will be able to split it into factors of the form. And we'll do plenty of examples with this, so if it's not sinking in because I'm using all these letters, that's fine. And ax plus b over ax plus bx, so ax squared plus bx plus c. So and this is to the I again. So what this is saying here is, if I have a rational function, so a rational function is this up here, p of x divided by q of x, polynomial divided by another polynomial, and again, the degree of the numerator is less than the degree of the denominator, I'm going to be able to split it up into things that look like this. They're going to be linear factors that are to some power, and quadratics to some power. And with the quadratics, you also get this, and we'll explain why in a second. So instead of, so because this is all really abstract, I'm going to do an example, and we'll see how this is used. But the point of this is, if you look at these two factors here, the a over ax plus b to the I and the ax plus b over ax squared plus bx plus c to the I, these can be integrated, and that's going to really help us. So these can be integrated to logarithms, usually. Logarithms, well, so if the power is 1, so let me not write that. These can be integrated either into logarithms or, powers. You can use U substitution for this. And you can use U substitution for this one also. So let's jump into an example. So this is example 2. So we want to find the integral of x squared plus 2x minus 1 over 2x cubed plus 3x squared minus 2x dx. And so, okay, so we're going to do partial fractions on this. And the first step of partial fractions is we're going to factor the denominator. So the numerator is not going to matter at first. We're going to factor the denominator. So I have 2x cubed plus 3x squared minus 2x. I can factor an x out of that. I get x, 2x squared plus 3x minus 2. This is x, 2x, and then x. So let's see. So we're going to want, so I think it ends up being this, x minus 1, x plus 2. So you can check plus 4x minus x is 3x. Yeah, so that works. So that factors like that. So what we have now is we have x squared plus 2x minus 1 divided by x, 2x minus 1. Sorry, get rid of that. So I'm trying to write divided by 2x cubed plus 3x squared minus 2x. This is equal to x squared plus 2x minus 1 over x times 2x minus 1, x plus 2. And this is the first step of partial fractions decomposition. I factor the numerator, the denominator. And now we move on to the next step. So what partial fractions says is I can take this thing, x squared plus 2x minus 1, divided by x times 2x minus 1, x plus 2. And I'm going to be able to write this as something that looks like this. A over x plus b over 2x minus 1 plus c over x plus 2. Where I do not know right now what a, b, and c are. So a, b, and c are left for us to determine. And we're going to do this using algebra. So this is an algebraic technique. So what we're going to do is we're going to take the right-hand side and we're going to put it all over a common denominator. And what is the common denominator of these three fractions here? Well, it's just going to be the product of all of them. So it's going to be x, 2x minus 1, x plus 2. And to get that common denominator, you're going to have to multiply this first one by the denominators of the other two. You're going to have to multiply a by 2x minus 1 and x plus 2. So we're going to do that. We're going to have a times 2x minus 1, x plus 2. And I'm really worried about running out of room here. Yeah, I'm going to definitely run out of room. So we'll make the screen a little bigger. And the same thing for b. If I want to put b over a common denominator, let me erase the highlight there. If I want to put b over a common denominator, I have to multiply it by x and x plus 2 when I do the common denominator. So then I get b, x, x plus 2. Same idea for c. I'm going to get c, and then I have to multiply it by the other two, x and 2x minus 1. C times x, 2x minus 1. All right, so what you'll notice now is I have, same denominator on both sides, so I can cancel that out. So those cancel. Now I'm going to have x squared plus 2x minus 1. is equal to a times 2x minus 1, x plus 2, plus bx, x plus 2, plus cx, 2x minus 1. And we're getting closer. So the idea behind this now is I want to write this, I want to take this right-hand side, and I want to make it look like the left-hand side. So what I'm going to do is I'm going to expand everything and then collect powers of x squared, x, and my constants. We'll see what to do from there. So let's do that. So I have x squared plus 2x minus 1 is equal to a times, and if I multiply this out, I'm going to get 2x squared plus 4x minus x is plus 3x minus 2. And b x squared plus 2x plus c times 2x squared minus x. There are faster ways of doing this. I just want to show every step here. So I have x squared plus 2x minus 1 is 2a x squared plus 3ax minus 2a plus bx squared plus 2bx plus 2cx squared minus c times x. And now I'm going to collect powers of x squared. So I have an x squared here, I have an x squared here, I have an x squared here. So the idea is, I can collect all those powers of x squared. I'm going to have a 2a plus b plus 2c. Let me make sure that my work is correct up until now. So it seems okay with that. And now I'm going to do the same thing for my powers of x. So let's use a different color. We'll circle my x's. So all of those are x's. So I could collect all those and factor out the x. And I'm going to have 3a plus 2b minus c. So I'm just collecting these and factoring out the x squareds, the x's, and now my constant terms. So my constant terms are the ones that don't have an x in them. And I only have one here. So it's just the minus 2a, right? So I can double check that, 3a, 2b minus c. Yep, so my work is good so far. And now the idea is, so if I compare these two sides, I have two polynomials here. So so this is x squared plus a constant, x squared plus x plus a constant. So the idea is, if I know two polynomials are equal for any value of x, so every value of x they match, then whatever the coefficients of, let's say, the x squared are, have to be equal. So that means, so if you look at the coefficient over here of x squared, what is that? Well, it's 1. I have 1 times x squared there. So what I can do is I can set those two coefficients equal. I can set the coefficient here equal to the coefficient of this. Because if these two polynomials are equal, those two coefficients have to be the same. So first I get 1 is equal to 2a plus b plus 2c. I do that for x squared, and now I look at x. So let me try and get rid of the highlight so I can use it again. There we go. So now I do the same thing for x. In front of x over here, I have a 2. In front of x over here, I have all this stuff, but they have to be equal if the polynomials are equal. So now I have 2 is equal to 3a plus 2b minus c. And the same thing for my constants. My constant here, -1, has to be equal to -2a. And that makes things a little easier for me, that last equation. Okay, so now we have to solve this system of equations. So the last one is the easiest to solve. That automatically gives us a is 1/2. And now I just have the top two, these two, to solve. And you can use whatever method you prefer. I'm going to use elimination by multiplying by factors that get things to cancel. You'll see what I mean in a second. So if I, plug in a equals 1/2 into the first equation, I get 1 is equal to a times 1/2. So 2 times 1/2, sorry, it's going to get 2 times a, which is 2 times 1/2. So that is now 1 plus b plus 2c. The second equation becomes 2 is equal to 3/2 plus 2b minus c. Now what I can do is if I look at these equations, I can see that if I multiply, let's multiply this equation by 2. And we'll see why in a second. So if I do that, my two equations are now 1 is equal to 1 plus b plus 2c. If I multiply both sides of the second equation by 2, I'm going to get 4 is equal to 3 plus 4b minus 2c. The reason I've done that is now if I add these two equations term by term, so 1 plus 4 is 5, equal sign just drops, 3 plus 1 is 4. B plus 4b is 5b. 2c minus 2c is 0. So it canceled out, which is what I wanted, because now this equation is really easy to solve for b. So if I do this, what I'm going to have is 5 is equal to 4 plus 5b. So 5b is equal to 1, so I've just subtracted 4 from both sides. And I get b is equal to 1 over 5. So far I have a and I have b. Now I can just take that and plug it into any of the equations I have so far. I can figure out what c is. So if let's plug into the first one, I have 1 is equal to 1 plus b is 1/5 plus 2c. So I'm plugging it into this equation that I just highlighted. It's at the top of the page right now. So I plugged it in, I plugged b in for that. I also already have a plugged in. Now I can solve this equation for c. So let's go ahead and do that. If I subtract 1 from both sides, I'm going to get 0 is equal to 1/5 plus 2c. So 2c is equal to negative 1/5. C is equal to negative 1 over 10. So according to my work, that is all correct so far. So now, why did we do all that? So, that was a really long process. Why were we doing that? So the point of this was, if I scroll back up, you can do this in the notes if you want, since I'm going to try and upload these. The idea was, I wanted to take, what I was integrating here, the x squared plus 2x minus 1 over 2x cubed plus 3x squared minus 2x. And I wanted to figure out how to split it up like that very first example at the beginning of this section was. There's at the very beginning of this section. The very beginning of this entire section, I took two fractions, added them together, and then asked what that integral was, and then I could just split them up like that. Here, I'm given something that I don't know how to split up. And the point was, I used algebra to figure out how to split that up. I now know that I have these a, b, and c values, so I can write now. So now I know x squared plus 2x minus 1 over x times 2x minus 1. So this is my integral that I was looking at, x plus 2. This is going to be equal to, so this thing is going to be equal to a over x plus b over 2x minus 1 plus c over x plus 2, where I've already determined what a, b, and c are. A is 1/2, b is 1/5, and c is negative 1/10. So let me just go ahead and write that one more time. It's going to be a over x plus b over 2x minus 1 plus c over x plus 2. And I've already figured that out. A is 1/2, so I'm going to get 1 over 2x. B was 1/5, yeah. So b was 1/5, so 1 over 5, 2x minus 1. And then c was minus 1/10. So I have a minus sign, 1 over 10 times x plus 2. And now each of these integrals is easier to do than this one was. So I had this integral to begin with, x squared plus 2x minus 1 over x times 2x minus 1, x plus 2. So this is the same integral I started with the bottom factored. This integral is the same integral as 1 over 2x plus 1 over 5, 2x minus 1, minus 1 over 10, x plus 2. And now each of these three terms can be integrated. And so I will leave some of that to you. So what you can do is, each of these, so you break it up into 3 integrals. I can do that since this is the integral. So this is 1/2 the integral of 1 over x plus 1, so dx, don't forget that, plus 1/5 the integral 1 over 2x minus 1 dx, minus 1/10 the integral 1 over x plus 2 dx. So if you do each of these, and I'll leave some of this to you, this first one we already know, it's ln of ln of the absolute value of x. This is going to be 1/10 the natural log of 2x minus 1. So that one you need to, so this comes from this second integral. You need to do u substitution if you don't see that. I got a factor of 1/2 that multiplied the 5 to give me a 10th. It doesn't relate to the third one there, the third factor there, the 1/10 that I just highlighted doesn't relate to that. But this last factor then is 1/10, and then this one is the natural log x plus 2, and then don't forget my plus c. In fact, let's just make the page a little bigger. And I'll write my plus c there. And that is my answer. So these are, again, it's a very long process. I've only done one example of partial fractions. I don't even know how long this video has been going because I'm not timing these. I know that I can't put another one in here because that's going to make it half an hour long. So I'm going to stop here. So just as a kind of a recap, because this was our first time seeing partial fractions, the entire point of this one is I started with this integral there, the x squared plus 2x minus 1 over 2x cubed plus 3x squared minus 2x. That integral I could not do to begin with. So what I did is I factored the denominator, and I went back to the fact that I can split the idea that I can split this up into these 3 factors when my rational function looks like that. And the idea is I need to figure out what those a, b, and c values are. The way I do that is I put it over a common denominator, because these 2 things will have the same denominator. Oops, sorry. Those two, so the left and right hand side of the thing highlighted at the top of the page will have the same denominator. And once I do that, I can cancel out the denominators, and I'm going to get 2 polynomials. And what I do is, so on the right hand side of this first one, I have everything. I have an a times something plus a b times something plus a c times something, but I want it to look like this left-hand side. I want it to look like, x squared plus 2x minus 1. I want to figure out how to do that. So I expand everything on the right-hand side, and I collect powers of x squared, x, and my constants. And from there, I say if 2 polynomials are equal, then the coefficients of the x squared term, so the coefficient of x squared here and x squared here, have to be the same. And that gave me this first equation here. And I do the same thing with every other term. The coefficient in front of x on the right has to be equal to the coefficient in front of x on the left. My constant terms have to be equal. That gives me 3 equations with 3 unknowns. Algebraically, that can be solved. So as long as you have as many equations as you have unknowns, as long as 2 of the equations aren't the same equation, this system can be solved for one solution, one unique solution for A, B, and C. So I go through and I solve those 3 equations for A, B, and C, and I can split this integrand that I had up into 3 much simpler integrands and do the integration that way. So I'm going to stop the video here. We're going to do, I think there are like 8 examples in this section. This one's going to take me longer to do than the other one. So if you have any questions about this, feel free to email me, leave a comment on the YouTube video. I'm pretty sure all my work is correct here, so there shouldn't be any comments about me messing up. But yeah, so if something is confusing to you, again, we're going to do a bunch of these. It should make sense eventually. So I'm going to stop here.